Thank you for the organizer for inviting me to take part in this meeting. My presentation will focus on performance of traditional buildings, and I'm about to present and to analyze the seismic response of historical Moroccan buildings in Atlas Mountain where the earthquake happened. So the outline of my presentation, I will begin by an introduction and then present the methodology and results before ending with conclusions and perspectives. On September 2023, we have an earthquake which struck in mountains of Morocco and causing significant devastations and causalities. The magnitude was about 7.
So you have to change the pages a bit back.
Yes. Sorry. The magnitude was about 7, and the earthquake was like 7 months after the earthquake in Turkey. So the economic loss is estimated to be like $7 billion, which is very significant for a country like Morocco. The earthquake has impacted about 3,000 villages, which are very scattered. It's not like here in Turkey. In Turkey, like you have a big city. And for the region, we have this kind of local architecture. It's stone masonry with 1, 2, 3 stories. This is actually pictures which we have taken after the earthquake. And this is about the village, which is like 10 kilometers far from the epicenter. We also have in the region this kind of buildings using rammed earth. We also use local timber for roofing and for reinforcing walls. The building which is our case study is Tinmel Mosque, which is an old building which is built like in the era of Almohad Empire. It is located at 17 kilometers far from the epicenter. It's located in a national road between Tarim and Marrakesh, as you can see here. So the building was constructed in 12th century at the era of Almohad Empire. The Almohad Empire actually has been also in the extension of the empire has been in Spain, Portugal, South Spain, and South Portugal. That's why we have similarities in techniques, construction techniques, and materials. The first building that has been built by the Almohad Empire was this one, Tinmel, our case study. And then there is the Koutous Mosque in Marrakesh, the Giralda Mosque in Sevilla, in Spain, and then the Hassan Tower Mosque in Rabat, the capital of Morocco. which has been destroyed by a known, very known earthquake, the Lisbon earthquake in 1755. Why we chose this case study to do the study? It's because actually it's represent typical architecture of the region. As you can see here, this is the village of where was born the leader of Almohad Empire, who is Bint Omart. You can say that we have typically the same architecture with square plan, with like central court. We can also see here the same kind of architecture is typically around Earth. Even when we introduce industrial materials, cement, concrete materials, the architecture does not change. So this is the building. The materials and techniques which were used to construct this building is rammed earth for the walls, reinforced using local timber, and for the minaret we have stone masonry using lime stabilized earth mortar. For the roofs we have wooden structures, and for the interior plastering, earth lime plaster. So the methodology of this study is a quick analyzing the design of the building to see if it complies with the guidelines regarding the what we call non-engineered construction of buildings. One, the principles of earth-resistant standards for this kind of building. We have the site construction, which have to be away from dangerous areas due to their geological and geotechnical conditions. Number two, we have the footing, which have to be well designed and placed, considering the construction site topographical and geotechnical issues, characteristics. Third, the materials and the implementation has to be of required quality, taking into consideration the limitations of the mechanical performance of these kind of materials. The implementation, yes, this is for the implementation. The implementation for the maintenance also is very important. So regular maintenance has to be done so that we can keep structures in their original condition. And of course, the design of the buildings, it has be earthquake-resistant design, meaning that the earthquake-resistant architecture, the architects, when they are working on design, they should work together with structural engineers. The shape of the building has to be like simple, regular, and as symmetrical as possible. We need continuous bracing walls in both plan and elevation, monolithic structures with enough tensile and shear strengths, homogeneous and compatible materials in terms of stiffness. So mixing different kinds of materials can be source of problems. This kind of guidelines you can find in codes for non-engineered buildings. For example, for the placement of the building, it has to be away from the pressure stresses coming from the soil. The shape has to be simple. The ideal shape is circular one, and then rectangular, square, and rectangle. If we cannot do this kind of design, we have to use separation spaces between different blocks to make simple boxes. And this is like what we can do if we have a rectangular building with length very important compared to the width. Also, for each box, we have like 10 rules we have to respect. The first one is very important. As you can see here is number 1, ring beam connecting all structural walls. And number 2, lintel, which has to be reached deeply enough into masonry. Number 3, enough distance between openings. Number 4, enough distance between openings and all wall corners. Building with plenty using stabilized materials, which is stable in and not stable into water. Windows not too wide in proportion of the wall dimensions. Enough wall thickness in proportion to wall length and height. Good quality of materials and implementation, of course. Roof weight, it has to be not very heavy, and sufficient wall roof connections. Let's see now our building if we have these conditions. So here you have the site of the building. You have like a slope, very important slope in this direction. This is the south, north. In the south we have like a platform horizontal. We have no problems at this area. The west side also, but if we look at the north part, we have earth stresses pushing the wall in the north. This is very clear here, and you can see the slope in this side, in the river side. So this is, we have here stresses coming from soil, and then maybe land side. We also have the plinth, which is laking, and we can see here the humidity at the bottom of the walls, which can be weaken the walls. For the overall shape, it's quite simple, square, symmetrical. So this is good. We have some little mistakes regarding the directions of the walls. This is the restoration plan. We can see here we have a perfect plan of symmetry. Here we have difference between level between the north and the south side of the building, which is not good. If we consider each wall, we have here in the table the thickness of each wall, the height, length. When we calculate the height, the ratio of the ratio of height to thickness, we can see that the wall, the arcades A, are the far from what the limit. Also, the little wall we have here M for the minaret. It's very the thickness is very small. We have only the two walls, west and eastern wall, which is like with enough thickness compared to the height and the length. So we can say that the wall which is more fragile, more weak, the weakest wall is the north one because of its length compared to the thickness. The wall also we have for the minaret, the eastern part. This is the building before the earthquake, and you can see that after the earthquake we have effectively the wall which is in the north part which completely collapsed. The walls in both sides, eastern and western, are the ones which resist earthquakes, and you can see even here some architectural elements which are still there. For the minaret, we have effectively the western part, which is of very very small width, which collapsed. So it confirms that if we respect the guidelines, we can find in codes we have actually today in some countries, this kind of damages can be avoided. You can see here for the first picture you have the landslide, as I explained before. The thickness of the north wall, which is very small. We have cross building from the gate, which plays a role of buttresses, stabilizing the eastern and western wall. And we can see also here for the reinforcement elements using timber, which is not because of problem of durability. It doesn't play their role. I also want to point that the building has been restored many times. This is the picture in 1930s. First restoration work in 1994. Second restoration works in 1999. And this is the building before the earthquake. Weeks before the earthquake, there is actually a project of additional restoration works, and this is the result after the earthquake. You can see that the wall, which is very long, is the one who is completely disappeared after the earthquake. The walls from eastern and western are the one that resist earthquake because of the presence of cross walls of the gates that were stabilizing the wall like buttresses. And you have here the picture of now today we are working on the restoration of the building. So if we want to conclude about these typical mistakes, we have the placement and footing, which is not well done. We have the ring beam, which is leaking. We have the plinth also, which is leaking. The design of walls are not, the thickness are not enough, considering the length and the height. And some problems of materials and implementation quality, and also the lacking of wall roof connection in the majority of the building. This is actually typical mistakes we found when we look at the houses in the region. For example, for this building, you can see that the walls that are not supporting, are not wall bearing the roof, are those which resist earthquake. This one in front are the weakest one because it does not benefit from the more column stabilization effect. It collapsed because of out-of-plan bending. Same building. You can see here at the same facade we have the other part of the wall which does not collapse. It does not collapse because it's a wall that supports the weight of the roof. Same here, but with other technique construction, stone masonry technique. This picture I take yesterday here in Kahramanmaraş, and you can see the same result. The walls which are supporting the roof are stable. The wall which is not supporting the roof has been collapsed. So maybe the most stable type of roof is when it's like in pyramidal shape. So the four walls can support the roof. Same result here with stone masonry vault roofs. The walls which supporting the roof does not collapse. So for the perspectives, we are going to do numerical analysis of the buildings. Maybe we will collaborate with our friends from Portugal. We are working also on writing the guidelines for retrofitting of this kind of buildings, non-engineered buildings, and also for the implementation and good practices for the implementation. We are working to produce short videos for self-construction, because let me explain, in our case in Morocco after the earthquake, the approach is different maybe compared to the other countries, because we involve local communities in the process. How we assist them with architects, civil engineering meaning structural engineering and geotechnical engineering. We gave them the design plan and we assist them for the construction. But it's self-construction. Why? Because it's a rural region. We cannot put all the communities in the same place, and also because they are local. They have activities like agriculture, and they need space. If I have more time, I can more time. 5 minutes. Right? Okay, just for this is some examples of what? No, not the video. This is the kind of drawing we are making to explain how to retrofit traditional buildings. For example, here, if we see that the building is if we see that the ring beam is leaking, we can make it like this, and this is for supporting the walls which are very long, so that when the next earthquake came, the wall will not collapse. This is the restoration of the corners of the buildings, because we want also to preserve the existent structures. For the short videos, we have this a prototype of buildings. This is it's a small buildings to take pictures, videos, so that we can make these short videos I have talked about. This is the images we take. And this, we use this geogrid materials to reinforce instead of wood, because wood is not durable in these conditions. We use geogrid materials. This is for rammed earth technique, fired bricks masonry, reinforcement of the corners, Adobe masonry. And this is for the ring beam. We use geogrid material with limes. It's lime concrete. It's not cement concrete. And this is for the ring beam using timber with connectors to the wall. So it cannot move when the earthquake comes. And also we involve in this kind of projects students and architects, engineers, so that they can learn new things, what we can do to make traditional buildings more resilient, more resistant to earthquakes. And this is the building at the end. We also experienced some tests, field tests to better implement materials, to better choose good materials. So thank you for your asking.